Hello, welcome to the SNIA Persistent Memory and Computational Storage Summit 2022. In this session, we are going to talk about SNIA SDXI Technical Working Group's foray towards standardizing memory data movement. SDXI stands for Smart Data Accelerator Interface. I'm Shyam Iyer. I am the chair for this technical working group in SNIA. I'm also a distinguished engineer at Dell. So before we get started, here's a quick agenda that we're going to cover. I'm going to talk about the current memory-to-memory data movement standard. I'm also going to talk about some of the application patterns and the benefits that we see with accelerating memory-to-memory data movement. I'm going to introduce SNIA's SDXI Technical Working Group, its goals and tenets to you. I will give a brief description or introduction to the internals of the SDXI specification. I will also introduce you to the SDXI community so you can network with them outside of these forums. I will also describe some of the futures that SDXI is going to invest its time in. Finally, I will give you some of the references, links, and announcements that you would like to chew on for further information around the specification and its technology. Let's look at what is our current memory-to-memory data movement standard. Software-based memcopy is our current data movement standard. Why? Because it relies on a stable instruction set architecture. Our challenge is it takes away from application performance because the compute cycles are used up in performing those memory copies. It incurs software overhead when trying to provide context isolation layers, whether it be between two applications, two containers, or two VMs or more. It's not like offload DMA engines is a new concept. We've had that for a while. Our challenge is their interfaces are very vendor specific. There is no standardized user level software that can make use of accelerators. Let's look at how acceleration can actually help us. And then we will talk about why we should go to standardizing. Let's look at one application pattern here. An user wants to move data from a source memory buffer to a destination memory buffer. As you have imagined, the application will perform software-based memory copies to perform this operation. But this takes away from the application performance. Let's look at how an accelerator can help you with this kind of a workload. So in this example, the application describes its work in a descriptor and inserts it into a descriptor ring. Then it notifies the accelerator with a doorbell that you have new work to do to perform memory copies. The accelerator reads the descriptor and then performs a DMA-based memory copy from a source memory buffer to a destination memory buffer. Once it's done, it sends a completion to the application. All this while the accelerator was performing the memory copy, the application could schedule itself to do something else. With this, you can see that hardware-based memory copies can be offloaded, and the application performance can be improved by letting the application perform other tasks while the memory copies are happening. Let's look at another application pattern. In this example, the application wants to store data into persistent storage. So the application performs a memory copy from its user buffer to a kernel mode memory buffer. And then the kernel instructs a kernel mode driver to perform a data transfer from the kernel mode memory buffer to the storage device. The driver may perform a memory copy into a DMA-able buffer and then issue a NVMe or a storage write command to the device. The storage device may read the data buffer. Once it's done, it will send a completion saying that the storage device has taken the data. Now, if the application wants to copy the data back into another buffer, it would again make use of the kernel mode driver to issue an NVMe storage read command, and then perform the storage device will process the command and then do a DMA write into a destination memory buffer, most likely a DMA buffer. Then this buffer needs to be copied into another kernel mode memory buffer. And then finally, the application will copy it back to a user space buffer. As you can see, there are lots of multiple data buffer copies can occur before the actual data movement can happen, from a source buffer to a destination buffer. So an IO device using a DMA is also like this, is also not ideal for performing data movement. We have optimized the persistent memory use case such that now you can store data from a source memory buffer to a persistent memory buffer with just the help of a memory copy. And vice versa, you can retrieve data from a persistent memory buffer to a source memory buffer. But as you have guessed it, this type of pattern also involves using memory copies to perform store of data to persistent memory buffers and retrieving of data from persistent memory buffers. How can we further optimize it? We can do this with the help of an accelerator, where the accelerator, just like in the previous pattern, takes the doorbell, takes the command to move data from a source volatile memory buffer to, say, a persistent memory buffer, which is the destination buffer. And once it's done, it can send a completion signal. So with this example, we have accomplished two things. We have reduced the number of buffer copies, but we have also offloaded the memory copies with the help of the hardware. Let's look at a third example. In this example, the application pattern, a guest virtual machine 1 wants to move data from its user space application buffer to another user space application buffer in guest virtual machine 2. Let's see how this will get accomplished. This buffer will get copied to the kernel buffer of guest virtual machine 1. And then the kernel may use a kernel mode driver or some other IO device to perform a DMA read of its buffer. The IO device, once it performs a DMA read, may send it over a network or a IO fabric to another IO device, likely the same device if it's on the same system. And then this device may write that buffer into a kernel mode buffer. And then finally, another memory copy is performed to copy it from the kernel mode buffer to a user space application buffer in the guest virtual machine 2. As you have seen, the context isolation layers that we have introduced between virtual machines also introduces multiple buffer copies. How can we optimize this? If we had an accelerator that could read the buffer from guest VM1 and write it to guest VM2 without having to do multiple buffer copies through the context isolation layers, we will have a much better performance. The key thing to note here is the context isolation layers remain, and the hardware is able to perform these memory buffer copies, efficiently translating those addresses from guest virtual machine 1 to guest virtual machine 2. Let's look at something else that is helping our case here. An application generally deals with data in use memory. Data in use memory is generally in DRAM. But last few years, we've been seeing the data in use memory being expanded to now also include persistent memory, CXL attached memory, memory behind IO devices. This means that the data in memory use is being expanded to all these different tiers of memory. Combined with the fact that we have diversity in accelerator programming methods, we need a standard that can work across all these different memory tiers using a standard way. Let's introduce SNIA's SDXI efforts here. Smart Data Accelerator Interface, SDXI, is a proposed standard for a memory-to-memory data movement and acceleration interface that is extensible, forward compatible, and independent of IO interconnect technology. This technical work group was formed in June 2020 and tasked to work on this proposed standard. We have 28 member companies and 80+ individual members working in this group. And this is what its vision is. SDXI is trying to bring the same kind of architectural stability that instruction set architectures provided for software-based memory copy, while preserving some of the security architectures in play in some of the modern platform technologies. It's attempting to eliminate some of the software context isolation layers when performing memory-to-memory data movement, at the same time allowing direct user mode access from the applications. While doing so, the SDXI design envisions different classes or tiers of memory, part of the system physical address space, whether it's DRAM, persistent memory, memory behind I/O devices, or CXL attached memory. SDXI design is also form factor independent, which means that an implementation could be possible in a CPU integrated implementation, or a GPU device, or an FPGA device, or a smart I/O device. When we build a standard specification like this, we can now innovate around the spec. We can add incremental data acceleration features that leverage the same standard. Let's double click on the design tenets furthermore. We are saying that data movement can occur between different address spaces, which includes user address spaces in different virtual machines. Data movement should also occur without mediation by privileged software, of course, once a connection has been established. It should also allow abstraction or virtualization by privileged software. We want to provide the capability to quiesce, suspend, and resume the architectural state of a per address space data mover. And why do we want to do that? Because that enables us to live migrate virtual machine between servers. We also want to enable forward and backward compatibility across future specification revisions. With this, interoperability between software and hardware can be made possible. We also want to incorporate additional offloads in the future, leveraging the same architecture interface. And this is important for things like computational storage, where it can use an SDXI device for many of its computational storage needs. It's also a concurrent DMA model, which allows for scale and flexibility with different implementations. Let's look a little bit into the internals that we have described in the specification. On my left here is an SDXI function. This could be a hardware function or a software emulated function. And this function will expose its MMIO space to manage, to program from a context perspective. SDXI describes two levels of context tables, which are managed by privileged software. These context tables point to various contexts that are being managed by the function. These contexts are controlled individually, and they have their own states. These contexts point to a descriptor ring through which a producer may enqueue work for the SDXI function. To make sure that the producer and the SDXI function are in sync, there is a concept of a write index and a read index. Write index is incremented when the producer inserts work into the SDXI descriptor ring. And then when the SDXI function processes these descriptors, it increments the read index. We also have a concept of a doorbell with which the producer can notify the SDXI function about new work being there in the descriptors, the rings. When you enqueue a descriptor, each of those descriptors may point to buffers on which the memory-to-memory data movement should occur. And the descriptors also point to a completion status block. When the SDXI function finishes the operation, it intimates the producer about the operation's success or failure by writing into the completion status block. To control which address spaces that the producer can target memory access to, there is a concept of an A key table. In the A key table, there are multiple A key table entries which identify the address spaces that the context can target for memory-to-memory data movement. This is on a per context basis. At the same time, the SDXI function also has access to an R key table, which stands for a receiver, which is more like a receiver access control. And this basically controls the resources that other remote functions may access on the local memory side. So basically, this is a little bit of a security protection to ensure that spoofing cannot happen from different functions that want to access the local resources. So the region that I have marked right now is the structures that are managed by user level software. So user level, all of these structures can be mapped directly into user space, and producers can send work to the function without having to get passed through multiple context isolation layers. The region that I have marked out with the outer boundary is the region that is in control by the privileged software. And for any kind of errors for any of the contexts that occur, way of for the SDXI functions to notify errors through an error log buffer. As you can see, all states are in memory. There is one standard descriptor format, and it's easy to virtualize. It's also accelerator independent. For PCIe implementations, there is an SDXI class code which has been registered, so we can have a common driver for that. So the memory structures also scale. So we saw the context tables are common for the SDXI function managed by the privileged software, but you can also have multiple contexts being pointed by those context table. And these various contexts have their own address spaces that they can target to, which is specified by the A key. The ring state is managed by user space, like we have seen previously. But there is one way to manage the error logs for each of those contexts. And then one way to control access to the local memory resources from the remote function, which is the R key table. And then finally, there's one way to start, stop, and administer all the contexts. So how does the descriptor ring work and look like? You may have seen in other implementations, the descriptors are processed in order by the function. It can get executed out of order and completed out of order. There are some control fields which specify how exactly they need to be processed, but the specification is designed for maximum parallelism of operations. The coalescing and serialization happened at well-defined boundaries. Between the read index and the write index, the function may aggressively read valid descriptors to improve performance. The indices themselves do not wrap, but there are finite set of memory locations for the descriptor ring memory buffers. The standard descriptor itself is very well organized. We've got a set of structures that define what and how the operation needs to occur. So the topmost V bit, the valid bit, indicates whether the descriptor is valid. Some of the control structures determine what kind of operation it is. Does it need to be chained? Is it something that needs to be serialized in a certain way? Should there be a barrier, kind of a sync that between different operations? And then we organize our operations into various operation groups. So as I'm showing you here, there is a DMA operation group, there is an atomic operation group, there is an admin operation group, and then there is a connect operation group. And within those operation groups, there are multiple operations that you can specify as part of your descriptor. There is also a completion pointer that points to a 32-byte aligned region of memory, which contains the completion status block. In this completion status block, we have a construct called a completion signal, which is initialized by software and decremented by the function on success. If the function detects an error, the error bit is flagged to indicate that the operation encountered an error. We have a lot of room for other bits in this 32-byte field to support future expansion of error codes. A little bit more into the descriptor format. There are some key attributes that are associated with the address. The address itself is a 64-bit address, and it could be anything from a host physical address to a host virtual address to a guest physical address or a guest physical virtual address. And it's always translated through the IO memory. The location for the data transfer is specified using the key identifiers, which is kind of what I'm calling the address space ID. This indexes into a specific address key table entry in the A key table. And we have some attributes that are associated with that address as well, whether the source or the destination is an MMIO space address. As we start targeting different types of memory classes, this becomes important as hints. The address key table entry itself encodes various address spaces and passage and interrupts that are available to that function context. So a descriptor that's part of the same context, any of the descriptors can reference an A key table entry for their specific operation. This is specifically the requester side control in terms of like, what do you want to do when you specify the operation in terms of which passage that you want to use to source or destination memory buffers. It also encodes something called an R key identifier. This is supplied to the target function so that the target function can index into its R key table and obtain an R key table entry. If a valid address identifier is found there, and this operation will be allowed. So it's kind of like a keying mechanism from the sender side as well as the receiver side. SDXI also has a concept of SDXI function groups. For cross-function address space to address space data movement, the functions must be part of an SDXI function group. So in your example here, I have an SDXI device with various virtual functions and another SDXI device with another set of virtual functions. In order for address space data movement to happen from, say, VF0 on device 0 to VF1 on device 1, they need to be part of the same SDXI function group. Let's look at an example of a multi-address space data movement within an SDXI function group. So in this example here, address space B is sort of a producer and because it has a descriptor ring and it's enqueuing descriptors for SDXI function, which is sort of the requesting function. It has an A key table and in which there are A key table identifiers associated with address space A and address space C, which means any descriptor can target address space A and address space C in its operations. So we have issued a descriptor and that targets the source buffer in address space A and a destination buffer in address space C. Inside our descriptor, we also encode the R key ID that will be now specified in the A key table. So the A key table has the R key identifier, and when this operation needs to happen, at least before the operation happens, the target function, in this case the source function A, needs to look up the R key table and the specific identifier there and make sure that this requesting function is allowed to access buffers or resources in address space A. This checks out, and the same thing needs to happen on the target function C as well, because that's going to be the recipient of a DMA write. And by consulting the R key table identifier there, this checks out as well. And so now a DMA read will happen into the source memory buffer in address space A, and a DMA write will now happen with the same data on address space C. So with that in your armory, I want to introduce you to the active community of the SDXI TWG members. It's my pleasure to say that a lot of the members have contributed in various ways towards improving the specification since initial contribution by founding members. Their contributions have resulted in improvements in many areas, like providing an architectural behavior for administrative start and stop operations, architectural context states and function states, improving cache injection mechanisms, having a deterministic discovery of the SDXI function groups, providing rich completion status and reporting, improving the mechanisms to control local memory access from remote functions. We have got general improvements around usage models and providing some interconnect agnostic specification language. Because remember, we're trying to be interconnect agnostic. So an SDXI implementation could be based off PCIe, CXL, or some other interconnect. And we have a growing list, an active list of contributors, and very, very thrilled with all of their participation here. As you can see from the picture here, they are across the industry, from OS vendors to OEMs to cloud vendors to IO device vendors to CPU vendors. So very, very excited with all of their contributions that they're making towards this spec. What can you expect from SDXI in the future? So we will definitely we are on track to release our version 1.0 specification. We are also planning on what activities we'll do post 1.0. Our current charter includes sort of new data mover operations for smart acceleration. And this is where we think that there is a lot of scope to collaborate with computational storage technical work group in defining what kind of computational storage devices may benefit from SDXI devices. And then we are looking at data mover operations that target persistent memory, make sure that all those targets can work efficiently with the SDXI interface. We are improving cache coherency models for data movers. We're looking at improving security features involving these memory-based data movers. And we want to improve the management architecture to work with these data movers, which also includes a connection manager which brokers data movement between different memories address spaces. Some additional topics that have been considered for post version 1.0 are RAS improvements, quality of service improvements, latency improvements. We've been discussing around how CXL-based implementations can take advantage of SDXI, and then generally improving heterogeneous environments to incorporate SDXI-based implementations. Here are some links that you may want to look for further information. We have the version 0.9 revision 1 specification available for review. These are some of the previous presentations that we have provided, and YouTube videos that you can go and look for. Something I want to highlight here, we have a new subgroup for SDXI and computational storage within SNIA. And the membership criteria for this subgroup is that you need to be a member of both the SDXI technical working group and the computational storage technical working group. And it's looking at an architecture that it looks at computational storage use cases with SDXI devices. In conclusion, I want to just say that data in use performance needs are increasing. Various accelerators and memory technologies are now in the market, and standardizing memory-to-memory data movement is important. So SNIA's SDXI technical working group is standardizing memory-to-memory data movement and acceleration. We have our first public version out for review, 0.9 revision 1. Please look at it, provide us with some feedback. Some of our TWG members have discussed in various forums about their motivations towards contributing to this specification. I would say that this enables persistent memory technologies even more, and also further accelerates computational storage use cases. With that, I would love to hear feedback from you all. Please take a moment to rate this session, and your feedback is important to us. Thank you.